Hi, and welcome to Real Physics. This is a YouTube show where I go over physics concepts, and today I will be going over one-dimensional motion, including displacement, velocity, and acceleration. So I hope you enjoy. Displacement is the difference in position between 2 points. The most common unit for measuring displacement is meters, but other units like feet and miles can also be used. Displacement can sometimes be confused with distance. To help explain the difference between these two terms, I will use an example. If I want to drive from my house A to my friend's house B, then I would take the road. The road between our houses is a curvy country road. Because of these curves, the distance traveled will be greater than the displacement. The distance traveled is the length of the road, while the displacement is the length of a straight line drawn from where I started to where I ended. Only by going in a straight line from where I start to where I finish will my displacement and distance be the same. In this example, the straight line was displacement and the curvy line was distance. Now that we understand the concept, I will show you how to use displacement mathematically. Displacement is most often seen as this delta x symbol. Delta x is equal to x final minus x initial. The delta symbol simply means change. In this equation, the delta symbol is used to signify the change between 2 points. X final and x initial are these 2 points in space. In our previous example, house A was x initial, while house B was x final. This equation will be very useful with velocity. Velocity is a measure of how long an object takes to change its position in a given direction. Velocity is similar to speed, except that speed does not include a direction. When you look at the odometer in a car, that is telling you the speed. Putting the speed together with the direction of the car is the velocity. Here is an example. There is a kid running a 100-meter dash. When the gun goes off, he immediately runs toward the finish line at a constant speed of 10 meters per second. Then suddenly, before reaching the finish line, he decides to run back toward the starting line at the same 10 meters per second. This seems like something that would never happen, but it will help us to see the difference between speed and velocity. Let us call the starting line x initial, 0, and the finishing line x final, 100. When the kid runs toward the finish line, he is increasing his x value or position. This means he has a positive velocity of 10 meters per second to the right and a speed of 10 meters per second. When the kid runs back toward the starting line, he is decreasing his x value or position. So his velocity is negative 10 meters per second, but his speed is still 10 meters per second. Velocity involves direction, while speed does not. Velocity is a measure of displacement over time, while speed is a measure of distance over time. Here are the equations. In physics, it is more common to use displacement and velocity than speed or distance. Let's use a practice problem to help us understand these equations. In my last video, there was a bear chasing a man. The bear was running at 20 meters per second, while the man was only running at 10 meters per second. If the bear and the man start 250 meters apart, then how long does the man have before the bear catches up to him? Well, let's use our equations to figure this out. When solving physics problems, I like to start with the goal. In this case, our goal is time. The variable we want to solve for is t. Now that we know our goal, let's list out everything we know and relate them to variables. The bear is running at 20 meters per second, so that's the bear's velocity. And we can call that variable VB to signify the bear's velocity. We'll do the same thing with the man's velocity, except call it Vm. We also know that the initial displacement between them is 250 meters. This is when it's useful to have an x-axis to set up our positions. If the initial displacement between them is 250 meters, then we can put the man's initial position at x equals 250 and the bear's initial position at x equals 0. So x initial m equals 250 and x initial b equals 0. That seems to be everything for our variables. So let's use our equations to relate these variables and solve for t. If we combine our equations for displacement and velocity, then we get v equals x final minus x initial over t. Since we have two velocities, then we can use two of these equations, one for the bear and one for the man. As we set up these equations, we should notice that we don't know the x final. Unfortunately, the x final for the bear is equal to the x final for the man because they will be meeting up at the end. Once we set up the velocity equations, we should have two unknowns. If the number of unknowns is equal to or less than the number of equations, then we are ready to solve. With some basic algebra, we can solve for t. The answer should be 25 seconds. If you also want to solve for the final position, the correct answer for that is 500 meters. Now that we understand displacement and velocity, it's time for our final topic, acceleration. Acceleration is the rate at which an object changes its velocity. The most common form of acceleration is gravity. If I drop a ball, the ball will start at rest in my hand and then progressively increase its velocity downward until it hits the floor. Just like displacement and velocity, acceleration involves a direction. That is why gravity is typically noted as negative 9.8 meters per second squared. Oftentimes we hear how fast a car can go from 0 to 60 miles per hour. That is a sign of how great the car's acceleration is. The equation for acceleration is change in velocity over time, or a equals v final minus v initial over t. Another useful equation that relates displacement and acceleration is x final equals 1/2 a t squared plus v initial times t plus x initial. Let's use these equations with an example problem to help us solidify the idea. Going back to the bear chasing the man, before we assumed that neither the man or the bear were accelerating. Now let's assume that the bear starts running at 20 meters per second and also accelerates. At what rate will the bear need to accelerate to reach the man in 10 seconds? Using our equations relating displacement and acceleration, we can plug in the bear's time and initial placement. However, we don't know the acceleration or final position. For the man, we can still use a basic velocity equation and plug in the initial position, which is 250 meters, and the velocity. In this equation, we don't know the final position. Because we have two equations and two unknowns, we can then solve the equations. The final answer should be 3 meters per second squared. Now that we've learned about displacement, velocity, and acceleration, I will show the relationship between these principles. This is best done with graphs. Here are three graphs of the bear showing his acceleration, velocity, and displacement over time. The bear's acceleration is constant, so you'll notice that the line on the acceleration graph is flat. Because he's accelerating, that means his velocity is increasing during the chase. This is represented on the velocity graph where we see a constant increase in velocity. Because his velocity increases throughout the chase, the displacement from his original position will increase at an exponential rate. Calculus helps us to understand the relationships between these graphs because the velocity is a derivative of the displacement and the acceleration is the derivative of velocity. Velocity can also be seen as an integral of acceleration, while the displacement is the integral of velocity. A derivative is basically a tangent line. By drawing a tangent line on the displacement graph, the slope of that line will tell us the velocity at that point. An integral is basically the area underneath the line on the graph. By finding the area underneath the line of the velocity graph, I can find the total displacement of the bear. To really master these ideas, it is essential to understand calculus. That concludes our discussion of one-dimensional motion. I hope you enjoyed it. If you have any questions, feel free to leave a comment below. Thank you for watching and have a nice day.